Good morning, ladies and gentlemen. Welcome to Concurrent Session 8A. Today we are going to talk about a very important topic on unlocking climate indices. Today we are joined by Dr. Rhys Whitley. Dr. Rhys Whitley is the science lead for the pricing and analytics team at Suncorp and is responsible for directing the company's research into climate and weather extremes. A physicist by training, he has spent over a decade working in the field of terrestrial ecology and land surface science, looking at how climate and wildfire regimes have shaped Australian ecosystems, particularly Northern Australia. Since joining Suncorp, he has used his knowledge and experience and expertise to facilitate the use of climate analytics in driving the business and financial decisions and strategy around extreme weather. We are also joined online by Tatiana Potamina. Tatiana is a senior pricing advisor within Suncorp's natural perils team. Her professional interests encompass climate change and its impact on natural disasters, extreme weather, public health, and various domains of climate science. She also maintains a keen interest in data science, using machine learning techniques to improve the application of climate data. And we have a third author who unfortunately couldn't join us today, Lisa Yeh. Lisa is a qualified actuary with over 13 years of experience in the general insurance industry across Australia and the UK. She currently leads the natural perils pricing team at Suncorp, where she works with climate scientists, data scientists, and other actuaries to understand the impact of climate on communities. Most of Lisa's time outside of work is spent attempting to keep up with her toddler. She also tries to fit in a bit of crocheting and swimming where she can. Of course, we at the Actuaries Institute acknowledge the traditional custodians of land on which we meet. Without further ado, I'll pass on to Dr. Whitley.
Thank you very much. Thank you very much for inviting me to here today. It's great to be here. And for today's session, I'm presenting a brief overview of Suncorp's work in the climate space. And that includes an example of our climate capability, some of the recent developments we've made in the climate risk space in attempting to link the hazard to industry losses. So just to give a brief background on my team, myself and Tatiana and Lisa, we all sit in the natural perils pricing team that forms part of our pricing and analytics division. We're quite a dynamic team. We're made up of actuaries, data scientists, climate scientists, and engineers. And our task is to determine the risk cost or the technical premium of an asset in terms of its vulnerability and exposure to extreme weather or geological events. This is an incredibly challenging role. Extreme weather events, as you know, are by definition rare, and so the data that relates to customer impacts is incredibly sparse. We just don't have hundreds of years of data to work with to find that central limit of loss. Consequently, we rely quite heavily on the science behind the phenomena we're trying to understand and quantify in getting to that true risk. And this is supported through the use of climate and hydrological data sets, catastrophe models that can infer the plausible physical limits of extreme weather and what the subsequent financial losses might be. So we've invested quite heavily in trying to bring the strengths of insurance and science together to be highly successful in this space. So in addition to pricing natural perils risk, our team's unique and specialist skill sets and knowledge means that we're also the source of truth in the business that's relating anything to climate and weather, and so we support these other functions. This includes reporting to the board and the group executive on the seasonal outlook and providing them inference that they can make strategic decisions on. And we also support our disaster response team in weather monitoring and understanding the events as they unfold. We're also an active participant in supporting scientific research in the science community. In a selfish way, this is for us to understand the true risks of weather extremes more than we do, but also we like to repay this in kind by providing our own expertise and data to help try and push the science forward. And finally, we act in an advisory role for all climate change related work undertaken by the business. So this includes climate disclosures to the market, the APRA CVA work, and even our own experiments that try to quantify the future risk that isn't necessarily a regulatory requirement. Now, serving all these functions in the business is quite a heavy load, but it's necessitated over a decade of investment in the resources and technology to support this high-end capability. Some of these investments have included, as I've mentioned, having a broad hiring policy, so we do hire outside the traditional actuarial space, and we invest and participate in the scientific community. But we also build up an immense catalogue of hazard and vulnerability data that we source through many sources, be it public, our vendors or partner investigators. And the idea is that through a lot of our AI model development, we can take a holistic view of all these multiple sources to come out with the what we perceive to be the best estimate of the risk. And finally, we utilize a lot of cloud technology. A lot of what we do just isn't possible without it today. So this gives us access to the cutting edge software and scale with the demands of the problems we have to solve. So this investment has allowed us to form, what I believe anyway, is an industry-leading understanding of natural perils risk in Australia and what the associated costs are around that risk. And it also places us in a very good position to be able to look at how extreme weather is changing over time and what the implications might be on our natural perils pricing going into the future. Now, the traditional idea of pricing of natural hazards is predicated on the idea that risk can reliably be estimated from historical information, that all losses due to natural climate oscillations average over the long run. However, we know this is not necessarily true, probably never was. As the world continues to warm, with the continual emissions of greenhouse gases, our climate is becoming more extreme and our weather more severe. The frequency and severity of natural hazards is beginning to emerge outside the range of historical experience that we would typically price on. So this presents to us a fundamental challenge as an industry, as our views of these risks traditionally as a stationary process are not. So what is true for the last 20 years is very unlikely to hold entirely for the next 20 and further, particularly as the dynamics and thermodynamics of the Earth system alters in response to global warming. So more frequent, more severe events will degrade profitability, access to reinsurance, and consequently raise premiums. So we need to investigate this. Now, further complicating this picture is that all risks are shifting at the same rate, or in the same direction, or are geographically uniform. So one should not expect everything to get worse everywhere. The picture is much more complex and requires a proper investigation of the geographical risk through time to understand how the risk landscape is changing and what the implications might be for our pricing. Now, just to give some illustrative examples, you don't have to understand those figures, they're just to show that I've got them from an authoritative source. So some examples are with tropical cyclones. So the current understanding is that we're beginning to see a decline in the frequency of events over time, but when they do occur, will become more severe. This is only true for some basins around the globe. It is not uniformly true. It has only been observed for the Northwest Pacific, at least in the observable record. Concerning coastal flooding, there is a development of low-risk regions that becoming moderate to high risks as sea levels continue to rise. And I point out what is perceivably a small increase in sea level rise of a metre. Doesn't sound like much, but that would result in significant inland inundation that is up to 200 metres. So the purpose here is to share with you some of the work we are doing at Suncorp, investigating and monitoring this changing risk landscape. So how do we quantify this change in terms of a climate risk factor for the various perils that we would rate for? Well, one of the solutions we have utilised is through the construction of climate indices and exploring their temporal and geographic behaviour. Now, climate indices are incredibly useful tools for investigating risk that provide a consistent and standardised way of measuring and comparing risk across time and space. They are able to distill complex gridded climate data into single indicators that would typically have thresholds, if exceeded, signify that there's a high likelihood of an event occurring. They don't predict actual events, but what they do is they show whether or not the environment would support an event occurring, and you can just assume that chaos is the reason around it didn't happen or it did happen. And this does allow some probabilistic interpretation of the risks in question. Now, you can have an index of anything. There are very well-established ones in the scientific literature that we use. And they are already employed in some regards in this industry. For instance, the Institute do have a climate index that they publish to the community. When it comes to climate risk, we can use these indices to capture the consistent divergences from the historical average and whether or not we feel that trend is significant. So you really want to be identifying those anomalous signals and target where they're occurring. So I'm just illustrating an example of a climate index. This one's for hail. This one measures the frequency of days that would support a severe thunderstorm. And most damaging severe thunderstorms have hail derived, but there is a component of wind damage. But this one is a simple combination of two atmospheric ingredients that are necessary for a supercell structure to form. We have the atmospheric instability, the energy in the atmosphere, and the wind shear, which organises the storm. There are also, and this is the equation for it, there is an alpha and beta there, which are these two parameters that adjust for the melting height of the atmosphere. Put simply, though, if the left-hand side is greater than or equal to the right-hand side, you have the environment for a severe thunderstorm. Now, if you fulfill that equation with all your grid climate data related to those ingredients, you can build up this neat picture of the average hail risk there on the left, which by itself is very useful. It gives you a geographical understanding of hail risk in Australia, and you can price on that if you had nothing else available. But what is just as interesting, though, is what's there on the right, which is the change in that hail risk over time, which here is from 1979 to present. We can see that for most of Australia, the hail risk appears to be decreasing in number of days, anyway, that would support a thunderstorm. But there in the southeast and just around Perth, there is a slight increase, and some of that increase is significant. What I want to stress, though, is that the units of change are quite small. That's in the measured in terms of days per decade. So while it might seem like 4 days increase in hail environments is a lot, it's probably less than 1 for most places around Australia. And similarly with the decrease. I would also like to attribute that this is not a hail index we've derived internally. This is from Tim Rawpack at UNSW, who is an excellent thunderstorm scientist. We source our climate data, which we call reanalysis, from various respected international sources. The philosophy of our team has always been, when assessing risk, to consider multiple authoritative views, the wisdom of the crowd, if you will. So we source our data from the European Centre for Medium Range Weather Forecasting, NASA, the Japanese Meteorological Agency, and NOAA, and as well as the Bureau, but I just don't have a figure for them. Each source has its strengths and weaknesses, with some better able to resolve climate dynamics than others. But this tends to be that the higher the resolution of the grid, the better your data, well, the better you are to resolve these extreme weather events through climate indices. And the reason is that higher resolution grids are able to capture those extremes better. They don't smooth them out, particularly as they're getting those effects of topography. But this higher resolution data does come at a hefty price. You need the computing power and the storage to support it. So here I've got two examples. There on the left is the hail risk, and there on the right is the bushfire risk. So for the hail risk, you are better off using a high-resolution grid and probably paying for that computer power to get those views of risk. As you can see, the other reanalysis sources do not agree that strongly with it. But ERA 5 tends to be the gold standard for reanalysis at the moment. For bushfire risk, it doesn't seem to matter too much. There on the bottom right-hand corner, the NCEP, that's a 200-kilometre grid, I believe, and it still does okay at capturing that bushfire risk. Obviously, as you move into a higher resolution grid, you're able to identify more specific geographical regions, but if you just don't have the computing power to hold high-resolution data, you can go to a coarser product. So, building climate indices on that regard requires significant investment. While in principle they are simple to construct, in practice they do require an immense amount of computing power and storage to put together. We rely on our Amazon cloud services to do this. We spin up what is equivalent to a supercomputer, I suppose, and that does cost a lot of money, but it is worth it with this payout that we get. And it's also important to understand the data sets and the variables you're working with. I put up here an example of us trying to calculate convective parameters over New Zealand. While it was easy enough for the ERA 5 data set, when we moved to another real analysis source, it just didn't work. And the climate scientist in my team was able to diagnose why and fix it, and now we have a comparable product. So it's not a bad idea to have a broad range of knowledge and backgrounds in your team to be able to analyze and work with this type of data. So we have developed a total of 52 unique metrics that relate to each type of weather extreme that we rate for anyway at Suncorp, excluding earthquake, as that is geologically driven. And we've also developed a web-based platform to support all this information. So we just don't want to keep it in our pricing team. We also want to share it with the rest of the business. So our web interface allows underwriting, capital, reinsurance, and the disaster readiness teams to be able to access and use this data and make any inference they want from it. And of course, they can connect with us for explanations. And this is a sample of some of the trends we've been exploring for some of the hazards, where you can see that, again, not everywhere is significantly showing a positive increase. There are large pockets of Australia that are showing a relative decrease. Rainfall being one of the more uncertain ones. So, this leads me to my next slide. I've probably gone through this faster than I wanted to. Putting together this database, this wealth of information, has allowed us to now be at a place where we can start investigating questions around climate risk and the subsequent insurance impacts. And we've really been trying to see if we can establish functional relationships between climate information and event losses. So specifically, are insurance losses events predictable from the evolving conditions evident in the climate space? So part of the validation and the work we've been doing here has been trying to see how the grid evolves with the historic industry loss events. Those specifically that are registered in the Australian Insurance Council of Australia's catastrophe database. For the most part, the intensity of the climate signals relevant to the peril in question do emerge quite strongly around key events. And this is just a demonstration here of an expression of the FFDI, which is days greater than the 95th percentile over a 20-year period, during that December month of the Black Summer Fire. So you can see that it highlights it very nicely. And we find that this is a common thing among most of the perils, at least when we look at large-scale events, so those greater than $100 million in terms of an industry total. Smaller events, less than that, are much weaker, but there is still something there. Consequently, we have some intuition here that there is enough inherent information in these indices, in the climate space in general, I say, to build performative models on each peril, and we can express the change in the climate risk rather than just in the hazard, but also in terms of the cost, which is really important for the so what of us as a business. It's great to see that, well, not great, but it's important that we can identify trends in the hazard and where they are occurring geographically, but tying it down to an actual loss figure does there make it very relevant to how the insurance business perceives it. However, we found that using climate information, you must respect it. And what I mean by that is you're unlikely to ever build a useful model by taking only a part of the information available to you and throwing the rest away. So natural catastrophes that emerge from weather extremes are largely influenced by the conditions that have developed around the entire region. They are not the result of some one value at an hour in time at a unique point in the landscape. Even if you were to take a subset of the grid and summarize that information over a region, it would still remove important spatial information and those interactions that help characterize why an event has occurred. So there, consequently on the right, you really want to be considering the full climate space, which allows the maximum amount of information to be utilized and retained by the model to draw those important relationships between conditions and an event occurring. So to deal with all this spatial information does require the use of neural networks, at least what we found, as opposed to a lot of the classical machine learning methods, such as random forests, gradient boosting methods, and others. These other algorithms are not really designed to handle important spatial correlations that are inherent in the climate data. The deep learning and neural network families do provide a powerful way of accurately and efficiently recognizing complex patterns that can emulate the nonlinear dynamics and predict that spatio-temporal evolution of weather and climate. So in our recent work, we have been testing the effectiveness of convolutional neural networks as a way of training loss frequency and size models against our catalogue of climate indices in the ICA's catastrophe database. And these spatial correlations and the complex dynamics behind them in the climate space can be evidenced through looking at activation maps. And now these maps offer a neat way of visualizing those pixels that have a strong relationship with the event that has occurred. And I've just put a few examples here. This is Ash Wednesday from 1983. That did occur across Victoria and South Australia, particularly in the outskirts of Melbourne and Adelaide. And you can see that the weight of the pixels in those maps is quite strong in those regions. It also occurs in Perth, so it's not perfect. And then for the recent fires in Perth in 2021, again, those pixels were, the models are able to pick up that important information in the climate space around the Greater Perth region. So this is quite a cool thing. It allows you to visualize how well your model is working and if it's making sense, because otherwise most deep learning algorithms are a black box, but you can pull out relevant information to kind of test whether or not your models are understanding the physics that would otherwise be driving these events. So we've been able to build a set of frequency and size models for each peril, and this helps to explain the changing background of the hazard in terms of a risk cost. Just above there, I've got an example of the bushfire risk cost for the nation, and this is also broken down into cresta zones there on the right. Now, these models are by no means perfect, though you can see that from the time series that some events are underestimated and not even captured. However, the skill for the most part is reasonably good. And it also shows that there is some utility here for the business to use this in other capacities. So you could use it in a forecasting capability, for instance, and just be aware that there is some uncertainty in your model. So some of the future developments we're working on now to try and take this further is try and bring the temporal resolution down to a day. At the moment, we operate on a month. And that is because we're really constrained by the target data of the ICA's database. But we have got access to our own claims information. So there is scope here for us to do, I suppose through some transfer learning, a way of connecting the ICA database with our own internal claims history. We also want to move to high resolution grids as long as the compute can support it. And that would be Barra 2, which I believe is at 12 kilometers, and is a derivative of the ERA 5 reanalysis, so but calibrated to Australian observations, and ERA 5 land, which is, I believe, at 10 kilometers. And yeah, also to explore more efficient, deeper networks that can better utilize that climate information. I feel like we're only at the beginning here. There is a lot more that we could do in this space, given the resources we have access to and the data and the people in the team. And I should also point out that we've just recently, while we've done this for Australia, we've also done it for New Zealand. And I've yet to see climate indices for New Zealand. So this feels quite important, and we're excited to share that as well at a later date. So there's just some concluding remarks. The climate indices do offer a powerful way of quantifying that climate risk and showing how things are deviating from the historical average. It does require significant investment and skill in this space to be successful. There is predictive power in the climate information to be able to link it back to event losses. And capturing that full climate space is important if you want to do it. And you don't have an excuse anymore, really. Neural networks are quite accessible to the wider community. So I do have a demo that, if Tatiana is online, she can show an example of our web app that the business has access to and how they are able to access climate information themselves. I'm not sure how that's going to work. There she is. Hello.
Hello. I can share my screen.
Yes, please.
Can you see the screen?
Nope.
It's probably loading.
There we go. So this is a lot of work. All that climate information, that essentially almost 20 terabytes of data is synthesized into this web portal for the internal Suncorp business. So Tatiana, do you just want to show some examples there of the different perils? It's going to move a bit slow. The idea is that all the indices we've calculated are accessible through this interface. You are able to go through the time series for every peril. You can cut it in temporally in terms of an annual summary, or you can go to month or season. She's just showing right there. It's able to give an average view, the climatology, but also the trend and the significance. We can also subset the information to different map views, spatial views. So we have catchments, which is very useful if you're looking at extreme rainfall, but crestas, which is very relevant to our underwriters, and there's also climate zones, and you just keep going up. The tool is incredibly interactive, so you can click on a cresta zone there, and then you'll get the time series information. We can also weight the indices based on exposure, so where people live, or where Suncorp has customers. Again, there on the left, we have the time series, but it's also cut up in terms of a heat map where it shows the months of the year across time. So you can see where things intensify for particular perils throughout the year. And there we go, we have the loss modelling there that Tatiana's put up for bushfire. So all this information is condensed and made as accessible as possible to the rest of the business. I guess you can go, Tatiana, to the risk index. Problems, you end up with too many windows, all these features that keep getting added. So we have, again, multiple sources, and we've just provided a way where you can take an ensemble view across those sources. And you can come up with like a total hazard index, if you will. It's very simple. That would combine all those perils and across all those data sources. I think if you click that squiggly line in the top left-hand corner, Tatiana, it distributes to a preferred. And then if you click on the map of Australia, you end up with this hazard or climate risk, overall climate risk metric over time. You can see it doesn't really move much. But that's probably not far off the truth. We don't expect the hazard is moving at such a rate that you would see a strong trend, but it's certainly there. And of course it gets smoothed out when you take it as a national figure. But I think if you go to a Cresta view, you'll see that it is very, very different. Yep. And I think if you want, we might be able to show New Zealand as well.
Yeah, I'll just need to open it separately.
I think if you just, you can use this one, just do dash, where it says climate index. I think it's _NZ.
Oh, I'll try that.
And then remove the, yeah.
Yep.
There you go. So we also have it for New Zealand. So the other part of our business, Suncorp is a trans-Tasman insurer. We've also built this out for our New Zealand stakeholders. So I'm happy to, from here, answer any questions you might have. Thank you.
Great. Thank you, Reece. And look, we've got the Summit app. So if you'd like to ask a question, please type your question by clicking on the Q&A icon. Now, if you haven't downloaded the app, I strongly encourage you to do so. You can find a QR code on your name tag, which I don't have in front of me, but you can do that. Now, if you're online, I believe on your right-hand side of your screen, you should already have the Q&A section. Sorry, let me get this. Okay, so we've got a few questions coming through, thank you. So, Reece, can we see the loss index, please, so we can see how the climate risk connects back to losses?
Yep. We can share screens again, or was the demo sufficient?
It was something that we didn't see in the demo.
Right, okay. Oh, yep. Yeah, absolutely.
Do you want me to share again?
Yeah. We can answer another question in the meantime.
I guess while you're doing this, I'm always fascinated by what you said around pixels and how most Australians live in major capital cities where the risks really differ from street to street and from suburb to suburb. So how do you control for that?
Yeah, it's a good question. I guess we predicate our index on the fact it's conditions. We're not trying to predict actual events. So if over Sydney per se, that for hail, for thunderstorms, if the atmospheric ingredients are available, you are likely to see a thunderstorm occur and that might have hail. Predicting exactly where that hail would fall it just isn't possible. Even if I had a higher resolution grid, there's so much chaos around hail, we couldn't do it. When it comes to something like flooding, you would need a hydrological model to see, I guess, suburb level impacts. The point here is just to kind of give that indication that what is driving these events, what are the ingredients behind them occurring, how are they changing through time? Because that is possible for us to identify, and it is somewhat supported by the science, at least. Predicting actual events would be too difficult, I feel.
So Mike Thornton has asked a question. So how far away from linking this to climate models to forecast possible insurance losses in future decades?
Yeah, it's a good question. So it is, yes, technically you can. You can go to the CMIP6 catalogue. You can go and get all those atmospheric ingredients, and you can calculate these indices under the various RCPs into the future. What is that information worth? The grid of a lot of those CMIP6 models is quite coarse. Probably wouldn't tell you much. You really need to be at 25 kilometres, I'd say, to resolve a lot of climate extremes, probably less. Not all CMIP6 models also are well calibrated to explaining Australian weather. So you end up with a very small subset to be used in this case. It is possible, but it's just what is it worth doing in the end? It might not give you anything.
So Ming Guan has a question. How do you evaluate and validate the performance of your deep learning models over time as new climate and loss data becomes available?
Tatiana, did you want to answer that question?
Yes, sure. So when we did the modeling, we have a validation data set, but we also set aside unseen data. So after the model was trained, we tested the results on this unseen data. And yeah, great question about new data, but it's quite a new project for us. So far we just worked with what we had, and as Reece said, we do have some improvements to make, and yeah, that's our next
It's
phase
probably
of work.
worth pointing out some of the difficulties we've had with using something like the ICA database. We don't get exact locations always for where events occurred. Sometimes it might just be in a state. So even if we can't say it happened in this pixel, we just have like, oh, vaguely happened somewhere over here. So that does limit its applicability. However, I wouldn't throw away that information. It's still observations. What we feel the way forward is to rely more heavily on our claims history. So we have very good geolocation on events, but still use the ICA's database to pre-train our models, give it a leg up.
Yeah, I guess related to that, as the climate continues to change and we see more and more of these severe events in coming years, do you expect the volume of data to enrich itself?
Yes, the resolution keeps going up. So that is presenting a difficulty. I believe ERA 6 may be a few years away, but that will then be at about 10 or 12 kilometre resolution. I mean, ideally they want to go to 5 and 1 kilometre. And I do not know how we're going to store that. Well, we can store it, it will cost money, but extracting that from ECMWF's services will be very difficult. It's very likely going to require us to collaborate more strongly with our scientific community who have those supercomputers and that data already available. So I think there's going to be a tighter synergy between insurance and science going forward as those demands increase.
So we've got a question from Ronald Lai. Does the model fit an underlying statistical distribution for frequency and severity, respectively, for future prediction purposes?
Tatiana.
Sorry, I had a bit of a, didn't hear the question correctly. Could you repeat it, please?
Does the model fit an underlying statistical distribution for frequency and severity for future prediction purposes?
with deep learning, you don't assume any statistical distributions. You just basically let model decide. So no, we haven't assumed there is any particular distribution. No.
A question from Cindy Lau. Do you find the commercial underwriters using your tool in pricing of their large accounts?
That's a good question. We know they use it, but they never give us feedback. So no.
But I guess, just among your partners, interested parties, do you find them showing interest in your tool?
Yeah, so we've had questions about underwriters contacting us, say mid-season, and they'll ask, maybe they're writing new business, what is the chance of hail and storms occurring for January? And we can give them that advice, and then we will point them to this website. We will walk it through with them and say, this is the information to support the statement we're making. We can get it, we might be wrong, by the way, but if you needed to make a decision and you want some evidence to base it upon, this is the way you can do it.
Lovely. And we're almost out of time, but Bryce Woodward has a question. Could you please describe the sequence of peril modelling evolution Suncorp has gone through over time?
It started long before I was at Suncorp. So I suppose before my time, a lot of the modelling of the physical risks wasn't done internally. We used to source it externally from vendors and other experts. But then things changed so that we started building that internal capability where it would be going to a climate index and trying to calculate that, incorporating it into our view of risk. We try and source flood, for instance. We do purchase various outputs of multiple hydrological model vendors, and we try and integrate a wisdom of the crowds approach of taking, not the average, but the best view possible based on this ensemble range of possible outcomes. And so that's where we've gone to, I believe. So where in the past, maybe 20 years ago, it was just one source and we consider that source the truth, we now try and incorporate that uncertainty and look at that central loss to make our assessment. Does that answer the question? I hope.
Great, thank you. Well, thank you everyone for coming to this concurrent session, and please join me in thanking Reece and Tatiana for giving us a great presentation.